Now we're going to get into what I regard as the really serious core of the study of fluid dynamics, fluid mechanics, which we're going to study obviously moving fluids, things that mechanical engineers are interested in mostly, and but studying them based on the differential equations. So this is the really truly rigorous way of studying these systems, the way you get true information, the way you can model things very accurately without necessarily the kinds of assumptions that we've been making up until this point about things either being not moving or not having any viscosity or whatever. So this is the path towards true understanding. I've been impressed that sometimes students who graduate from this undergraduate fluid mechanics class don't seem to be very familiar with the actual differential equations that govern flow. So we are going to emphasize those pretty strongly. I think that if you can get to an understanding of fluids really from the differential equations, that will provide a deeper understanding for you to move forward within your lives, rather than sort of remembering a bunch of special cases. But they are challenging equations, and hopefully you'll see that by looking at them in a certain way, they can, although it should be challenging, can also be um, provide a lot of insight and be extremely useful. So we're going to start with what we're actually trying to model here. So the challenge with fluid mechanics is that you have a lot of variables. So the dependent variables in any fluid study are, rho, the density of the fluid, which of course can change, temperature of the fluid, which can change a lot of the properties, including, of course, rho. You have the velocity, which is a vector, so that's actually three variables in one, and you've got pressure. So these are, here's just spelling out the velocity vector. Usually it's represented either as u, v, and w for the x velocity, y velocity, and z velocity, or I think in the case of your book, ux, uy, uz, representing those three velocities. In order to solve for all these, of course, then we have six unknowns. So you need six equations. And so what are those six equations? Well, the first equation, not a surprise to you, we've used it already in this class, is going to be mass conservation. And so that's equation number one. Sometimes it's referred to as the continuity equation. So we have mass conservation or continuity equation. Those are the same equation, just different names for the same thing. We have three momentum equations. So there's going to be one momentum equation in each direction. Since we live in a three-dimensional space, we always have three different directions. Usually those will be x, y, and z. Of course, you can have three dimensions in cylindrical coordinates, theta, r, and z, or you can have three dimensions in spherical coordinates, r, theta, and phi. But whatever spatial coordinate system you're using, you're always going to have three different ones, and so you're going to have three momentum equations. Energy conservation, again, we have used this. We used the energy equation to derive the Bernoulli equation, but of course we neglected viscous effects, and that's a major restriction. So we're going to use the energy equation. And then finally, as your sixth equation, you have the equation of state. So this essentially tells you something about the fluid. An example of equation of state, of course, is the ideal gas law. So it gives you a relationship between pressure, temperature, and volume. All of these equations, essentially, or many of these equations, are nonlinear partial differential equations. So the momentum equations are nonlinear partial differential equations in particular. They are also coupled, which means that the solution to one equation affects the solutions to other of the equations. So these are extremely difficult to solve, even with a computer. So these are some of the most challenging equations to solve. Some of the most massive computers in the world have been dedicated to solving problems in fluid mechanics. We can't do that. This is not a course in computational fluid mechanics. You're certainly welcome to take such classes. Dr. Resi is an absolute expert in computational fluid mechanics, uses supercomputers, massively parallel processors to solve some extremely challenging computational fluids problems. But so you could study that here. You can get involved with that at any time. Start learning how to do that kind of work. But that's not what the focus of this class will be. We're going to make some assumptions in order to solve them, because you can't solve them otherwise. But there are certain cases where the assumptions are quite valid, and so we will be able to simplify these very, very complicated equations for very particular problems, where we can get exact analytical solutions for specific cases. One of the most common simplifications, we've already used it many times. Most common simplification is this incompressible flow assumption. So we've been talking about this almost since the very beginning of class, maybe since the beginning of class, that many, many, many of the flows that we are interested in as engineers are incompressible. There are plenty that aren't. I mean, if you want to study rocket jet propulsion, or jet propulsion in general, rocket propulsion, jet propulsion, those are compressible flow problems. The fluid is moving extremely fast, there are massive temperature changes. All of those things are going to cause changes in density that are quite significant. But for many, many problems in engineering and in life, you can treat rho as being approximately constant. And we have talked about when this is valid. It's essentially always valid for liquids, since liquids are almost always incompressible substances. So rho is constant for liquids. But, somewhat more surprisingly, as we've discussed, it is also true for gases most of the time. Rho is approximately equal constant for gases under the limit that we've talked about. If U max, the maximum velocity in the problem, is less than about 0.3 of the Mach number, and if there are not large t variations. So it's not about whether T is hot or cold, but if T is changing a lot in the flow, then of course gases will change their volumes and therefore change their densities. So it happens a lot. We've talked about that 30% of the speed of sound, at least at standard temperature and pressure, that's going to be about 100 meters per second, maybe a little more, 120 meters per second. But if you're in those more, that's pretty darn fast. So if you're in flows that are not really, really fast, we're not talking about jet airplanes. If we're not talking about jet airplanes and rockets, and we're not talking about large T variations, the incompressible flow assumption is usually a pretty good one.